Hello, I'm Richard Moore from NASA's Langley Research Center in Hampton, Virginia, and I'm here to talk about the North Atlantic Aerosols and Marine Ecosystem Study, which is a 5-year NASA study trying to understand the interactions between the ocean and the atmosphere over the North Atlantic. And before I begin, I just need to acknowledge that this work was done by a large number of collaborators, both at NASA and other government and university research institutions. And so why the North Atlantic? And so a good motivational slide is this animation that's put together from CWIF's imagery showing the change seasonally in the ocean chlorophyll and vegetation index throughout the year. And so as we watch the seasons come and go, what really jumps out at us is this bloom that seems to pop up every year in the springtime over the North Atlantic, the naturally occurring, annually occurring phytoplankton bloom. And so despite the fact that we can see this bloom happen every single year from space, actually the dynamics of why this bloom comes about remain somewhat controversial. And so a major goal of NAAMES is to try to understand those bloom dynamics and understand how the winter seasons set up the spring season for that large bloom. In addition, while we're looking at this from the satellite perspective, we also know that those swirling colors of greens and blues are actually made up of individual phytoplankton and zooplankton and other ecosystem and ocean biological constituents. And so we wanted to understand the really detailed ecosystem view of what's occurring there throughout the year. We also know that what happens in the ocean doesn't stay in the ocean, and that through the processes of wave breaking and bubble bursting, as well as the emission of volatile trace gases that can go on and be photooxidized in the atmosphere, that the ocean is a major source of cloud condensation nuclei that can nucleate cloud droplets. And so understanding the composition and abundance of these aerosols that are able to be CCN is also really important for linking what's happening in the ocean to the broader atmospheric radiation budget and climate. And so to study this, NAAMES is a 5-year study that is just wrapping up this year from 2015 to 2020. And we use 2 global class assets. The Woods Hole Oceanographic Institution research vessel Atlantis, which is shown on our left, and the NASA's C-130 Hercules, which is shown on the right. And so each of these assets would go out, we would go out into the North Atlantic during different seasons, and we would look at the latitudinal gradient of the phytoplankton bloom. And so this is a typical map during a bloom period of ocean chlorophyll. And superimposed on that is the black sailing trace of the research vessel Atlantis as it leaves Woods Hole, Massachusetts and steams eastward to roughly about 40 degrees west longitude. And then we would do this north-south line profiling the latitudinal variabilities, the spatial variability in the phytoplankton bloom. And so we would do this not just for one season, not during the bloom when everybody else has done these studies, but also during the shoulder seasons and the winter minimum in order to understand how changes in the phytoplankton and the ocean ecosystem composition give rise to the resulting variability that we see in this annually occurring cycle. And so just to highlight some of the instruments that were on the research vessel Atlantis, we have a number of different in situ aerosol and trace gas measurements that were mounted on the bow of the ship in these large white shipping containers. And they would draw air in through these large snorkels that were raised up above the ship in order to get out of the sea spray zone. So we're not just capturing those droplets coming off the surface, we're actually getting the aerosols that are persisting in the atmosphere. We also had the unique capability from the NOAA PMEL Sea Sweep in order to look at primary marine aerosols in their floating sea sweep bubbler. In addition, there were a whole host of other different experiments targeting the sea surface microlayer. We had autonomous floats that the ship would deploy as sort of breadcrumbs to look at the water evolution after the ship left, and then a variety of other different ocean biology focused experiments. In addition, on the NASA C-130, we had a suite of remote sensing and in situ instruments. So some of the remote sensors are shown on the top right. We had a high spectral resolution LiDAR, giving us the aerosol and cloud profiles in the atmosphere, a research scanning polarimeter, giving us much more detailed information about the atmosphere, but over the range of the column, and then an ocean color imager giving us the perspective of the ocean. And coupled with these remote sensors that we're looking down, we had an upward looking zenith remote sensor, 4-star, giving us the perspective above the plane. And then we had in situ measurements measuring the aerosols, trace gases, and cloud properties wherever the plane would fly. And so a typical flight pattern relevant for this talk focused on aerosol cloud interactions is shown here. So typically the aircraft would fly out to meet the ship in the middle of the ocean. We'd do an initial leg at the lowest flight altitude, about 300 feet. We'd profile through a series of stacked wall pattern level legs, the below cloud aerosol boundary layer, the in cloud properties, and then we would ascend to the maximum altitude of the plane to give the remote sensors a perspective of what was happening in the atmosphere below the aircraft. And so combined with those flight measurements, we also have the detailed measurements that the ship was taking, both from the in situ measurements at the surface, as well as an upward looking ceilometer, periodic radiosonde launches from balloons. And then we had the satellites that would periodically do overpasses, as well as the geostationary image looking down. And so an example of one such cloud module is shown here. This is for the November 12th, 2015 case. So this was the winter time conditions during NAAMES 1. So on the left, you can see a GOES image of the cloud conditions while we were doing this module. The ship is denoted by that blue diamond, and the flight track during this wall pattern is given by the red trace. And so you can see that we're in a very dynamic cloud environment, but we're focused on this area of more uniform cloud coverage. On the right, you can see as the aircraft moved back and forth, we assigned the endpoints of our wall pattern points A and B. And then at the midpoints, what I'm showing there with those white circles is using the aircraft measured wind speed and wind direction, how far the wind, the air that we measure at point M would have traveled as we are doing those repeated transects in time. And so you can think of that first point at point M when we did our level leg at the deck, and then that furthest point to the northwest as the point where the air came from for that last high altitude remote sensing leg. And so looking at the vertical cross section on the right here, we have the flight track again, a long track distance from point A given by the red trace. And now I've overlaid the cloud droplet probe droplet number concentration expressed as the blue dots. And what we can see is that the cloud is a very narrow layer between 1 to 2 kilometers, and that we're doing an excellent job capturing the below cloud and above cloud clear air portions, and that this persistent and very stratified cloud deck is very consistent with the thermodynamic profile that we get from the radiosondes, this increase in relative humidity as we approach the cloud level at 1 kilometer. And then once we get above cloud top, we see the effect of that aversion and the drop off in the relative humidity. And this is again, very consistent with what we get from our upward-looking ceilometer LiDAR measurements, as well as our downward-looking high spectral resolution LiDAR measurements. Again, some glimpses here of the cloud base and the cloud top. Again, very consistent with that 1 kilometer to 2 kilometer cloud range, although the ceilometer gives us the perspective as well that we might be seeing some evidence of drizzle throughout the time period that we were making these measurements. And so we have this detailed information of the aerosol, the cloud, and the dynamics over the course of 3 different NAAMES cruises, 3 different NAAMES airborne measurement campaigns. And so this is showing the particle number concentration on a logarithmic scale for each one of the different cloud modules. And the solid line represents particles greater than about 10 nanometers measured by the CPC, and the dashed line is particles greater than 100 nanometers measured by one of the optical particle sizers. And really what jumps out at you right away is that while NAAMES 2 and NAAMES 3 are fairly typical of clean marine conditions, concentrations on the order of a few hundred per cubic centimeter, that the NAAMES 1 conditions were much cleaner, on the order of a few tens per cubic centimeter. And so we have some great dynamic range here in the aerosol loadings. If we look at the vertical wind velocity probability distribution functions, where the average here is given by those white diamonds, we see that there's a lot less variability over the seasons. And so we can combine these two and do some really interesting exploratory analyses using parcel model or parameterizations in order to tease out important features of the cloud, like the cloud maximum supersaturation, which we would interpret from this graph as being perhaps a little bit more microphysically driven by the low aerosol concentrations during NAAMES 1. And then we see a drop off in that max supersaturation during the higher aerosol loadings in NAAMES 2 and NAAMES 3. So just to sum up, NAAMES really provides a comprehensive data set, not only for looking at the ocean and atmosphere interactions, but also really specifically aerosol cloud interactions using ship, aircraft, remote sensing and in situ, and then tying it all together with the satellite imagery. We really have an end-to-end perspective of what's going on in the remote marine atmosphere. The fact that we covered 3 different seasons during NAAMES gives us a really large dynamic range in our aerosol and cloud droplet number concentrations. And we also have the supporting detailed meteorological information, including those cloud updraft velocity measurements that we need in order to effectively interpret this data set in a way that's meaningful for models. And so we're working on a Nature Scientific data descriptor that will summarize the 20 cloud modules that we completed during NAAMES 1 through 3. And so look for that in the near future. And in the meantime, I'd like to direct your attention to the NAAMES website, naames.larc.nasa.gov, where you can find more results from this study and also links to the data which are freely and publicly available. Thank you.